But first, one more interesting character in this study. De Broglie was a French scientist, all right, and he proposed that all moving objects have wave properties. Now, people, since Einstein had said, okay, well, yeah, electrons, maybe they'll have this wave-particle duality and stuff like that and do it, but nobody had thought that all moving objects have this. So what he did was really clever. One of Einstein's equations is E equals mc squared, and he realized that Planck's equation was E equals hc over lambda. And you'll notice that both of these have an E. So we essentially let mc squared equal hc over lambda. I mean, it's so simple, but he was the only one to think about it. Now, as you can see, you can cancel out one of the speed of lights. And because he's talking about particles, all right, or all moving objects, objects aren't supposed to move at the speed of light. This is another one of Einstein's thing. So what he did is he substituted in for the speed of light. Once he cut it out, he substituted in for the speed of light, he substituted in the velocity. So v here is the velocity in meters per second, all right? And in physics, this would be like how they measure how fast things go and stuff. And when he rearranged it, he got lambda equals h over mv. And at first you're like, oh yeah, whatever, that's great. But this is an object with mass, and the units for mass in this particular problem are kilograms, we're going to see. But anyway, an object with mass, and that object with mass traveling at speed v is going to have a wavelength. And if you saw me walking down the aisle of Fred Meyer's or Safeway, what this is saying is that in theory, you should be able to see me having a wavelength, like walking like that. And that's just like, what the? All right. And it's not because I've been drinking or something like that I'm like staggering around the aisles. All right. This is because objects with mass m should have wavelengths associated with them. And this like blew people away. Now, de Broglie was writing his PhD thesis, and he did this little E equals mc squared equals hc over lambda thing, and he basically created a 7-page PhD thesis. Now, I'm emphasizing this because my PhD thesis was like 400 pages, man. It took a long time to write. And this, he's 7 pages. Anyway, he sent this to his committee, and the committee really didn't know what to do with it. So they sent it to Einstein, who had talked about, well, maybe there's this wave-particle duality. Einstein looked at it and go, whoa. He goes, give this guy his PhD. And de Broglie became a powerhouse in science. And again, the idea behind de Broglie is that objects with mass m and speed v are going to have a wavelength associated with them. Whoa. This is an example of how this stuff works out. Let's say you want to calculate the wavelength of an electron traveling at 75% the speed of light. So objects aren't supposed to go the speed of light. That's one of the things that makes Star Trek people mad, but that's another thing. But anyway, it's Einstein's thing, and I respect Einstein. But anyway, so we're going to use wavelength equals Planck's constant h divided by mv. And if you throw these parts in, and you may have to look up some of these numbers, this number we talked about in chapter 2 part 1 real fast. This is the mass of a single electron, and it's certainly not a number that you have to know, but it's 9.11 times 10 to the minus 31 kilograms. We also talked about in the last section how a joule is what they call a derived SI unit, and a joule is a kilogram meters squared per second squared. So because the joule has the kilogram in it, the mass here has to be kilogram as well. Most of the time in chemistry, using mass in grams is okay, but not in this particular part. So use kilograms with de Broglie. Anyway, speed of light, we've already talked about that. 75% would be 0.750. So throw all of this in your calculator, and I do encourage you to do that just to make sure your math skills are good. You end up with a wavelength 3.23 times 10 to the minus 12 meters. And believe it or not, that is a wavelength which can be measured. It is a measurable wavelength for an electron traveling at that speed. Here's the note again, how a joule is a kilogram meters squared per second squared. And so you have to use kilograms for the mass in these problems. And again, most of the time in chemistry, using grams is no problem, but here you have to use kilograms.
Electrons have wave properties. If we shoot a beam of electrons through thin metal foil, the atoms of the foil cause the waves to interfere with each other. The interference, or diffraction pattern, can be recorded on photographic film as a series of concentric circles.
This is essentially a source of electrons. They call it an electron gun. And electrons are particles. They have the mass, that 10 to the minus 31 kilograms we saw earlier. And if this was a true gun and it fired a quote-unquote bullet, you would think it would go through the metal foil and go through to the other side and like hit right here, all right? And that would be it. But what you actually see is that concentric circle pattern. And that looks more like if you've ever thrown a rock in a still pond, the waves kind of emanate out of that. That's what it looks like. Electrons here are behaving like waves. There are lots of examples where waves behave, or electrons behave like waves. You'd think they were particles, more like the bullet from a gun, right? But in reality, there are tons of examples now of where these crazy electrons can be like waves, and that's totally cool. So let's go back to me walking down the aisle and maybe like swaggering, and you think, oh, is that too much to drink? No, it's just de Broglie. Well, anyway, you don't see me doing that, okay? And that's okay. So let's say that you wanted to find the wavelength of a baseball traveling at 100 miles per hour. So you'd use the wavelength equation for de Broglie, wavelength equals h over mv. Turn the grams into kilograms, turn the miles per hour into meters per second. And if you do that, you end up with a wavelength of 1.3 times 10 to the minus 32 centimeters. And that's an unmeasurable quantity by current technology standards. So we could not measure a baseball traveling at 100 miles per hour. We couldn't measure its wavelength. It's too massive and it's too slow, all right? Not gonna work. So that means if you see me walking in Safeway or Fred Meyer's, you won't see any wavelength associated with it, all right? I'm too massive, all right? I have too weird of a speed. You're not gonna see a wavelength for me. On the other hand, if you have an electron traveling at a pretty good clip, 1.90 times 10 to the 8th, getting close to speed of light, that wavelength comes out to be 0.388 nanometers. And those are the kind of wavelengths you can measure. So it's basically for electrons, really small particles, that de Broglie is appropriate. Electrons and light both exhibit wave-particle duality. And again, that means that both electrons and light sometimes will act like waves and sometimes will act like particles. So the electron doesn't act in that little animation up there like a bullet from a gun. It acts like a wave, and it goes through and makes that cool diffraction pattern. Pretty cool. Schrödinger was a major force in the development of wave or quantum mechanics. And again, Schrödinger is a really interesting kind of person. And he developed the idea of what's called a wave equation or wave functions. And they gave them symbols psi. And if you applied a certain type of math process, h, to the wave function psi, you would end up getting out the wave function and the energy, which was really, really cool. And they used quantized energy functions. So instead of having continuous values, which is kind of like this slope would be right here, and that's what classical physics says, you can actually only have discrete values. This is analogous to what Bohr saw with levels of the atom, all right? There are only certain parts that are possible. You can't have all of them. Schrödinger is really interesting, but most of the stuff from here on in is going to be the result of Schrödinger and his other colleagues' work. That psi is really interesting. It describes the motion of the electron waves with location and time. And that quantization thing comes out naturally. So while Bohr kind of threw it in and said, well, this is what works, Schrödinger actually saw that this comes out naturally. The math of Schrödinger is pretty intense, all right? And again, if we all had taken Math 254, we could talk more about these things. But we haven't, and that was never the intent of Chem 221. So just realize that when you do this higher level stuff, all of this comes out naturally. Here's some examples of that H psi equals E psi thing I babbled about earlier. And again, each of those psi wave functions has a distance and two angles. So if you've heard about like spherical coordinates or polar spherical coordinates and stuff like that, that's the kind of stuff that this will apply to. Now, more interestingly is that each of those wave function corresponds to an orbital. And an orbital is a term we're going to use here pretty soon. So like down here, this little psi, that would be an orbital. And when you apply the function, H function, to it, you get out some information, but the orbital comes back. And an orbital is just a region of space where the electron is found. We're going to start talking about orbitals here in a little bit, but without so much math. The wave function orbital does not describe the exact location of the electron. All right, we're going to see that the wave function orbitals are really good for finding the energy, but not so good for finding the location. However, because it's nice to know what the approximate location is, if you square that wave function, you get the probability of finding an electron at any given one point. So imagine that you have an office, all right, an office with a computer. Probably most of the time, you're going to be close to the computer. So the psi star of that room, your office, would say that most of the time you're by your computer. But once in a while, maybe you're on the opposite wall looking out the window, all right? Or once in a while, you're down in the kitchen getting a drink, all right? Psi star just shows the probability of where you're going to be, but it doesn't always show you where you're going to be. We're going to see pictures of orbitals pretty soon that look something like a figure 8. And those figure 8s mean that most of the time the electron is going to be somewhere in one of the orbs, if you will, of that figure 8. But once in a while, the electron might be way off to the right, or maybe once in a while, it'll be looking out the window right there. Realize that psi star, the probability, is most of the time correct, but not all the time correct. And that's another interesting thing about quantum mechanics. One final person is important to talk about, and his name is Heisenberg. Heisenberg was actually a person that worked in Germany during World War II on their nuclear bomb. And depending on who you talk to, Heisenberg was either a passionate person working on it, or he was trying to prevent them from developing it. And I don't know what the answer is. But Heisenberg did come up with a really interesting idea called the uncertainty principle. And how he got this is quite complicated. But anyway, what the Heisenberg uncertainty principle is all about is that you can't simultaneously know the position and the energy of an electron at the same time. It's really not just energy, it's momentum. Momentum is mass times velocity, but you can see in science that momentum and energy are closely related, so people usually think about it as energy. So you can't know position and energy of an electron at the same time. Like you have to make a choice. You can know one or the other. Now, chemists in chemistry, we're always interested in the energy, all right? So if it comes to the choice, the chemist will want to know the energy of the electron as close to a value as we can. But if you pick energy, then that means you don't necessarily know the position well. So we might know exactly what it takes to go from n equals 1 to n equals 2. All right, that delta E, we've got it nailed down. We've made that choice. However, if it comes to an electron in an s orbital, which basically look like spheres, all right, most of the time it's going to be within that sphere somewhere. We don't know where, but most of the time it's going to be inside there. But even most of the time means once in a while it'll be outside there, or maybe down there, or up here, all right? It's going to be all over the place. So Heisenberg's uncertainty principle says we have to make a choice, and we choose as chemists energy over the position. So there's always going to be a little uncertainty about where the electron is. Heisenberg, like I said, some people think he was a hardcore Nazi. Other people say he was trying to prevent the Nazis from developing the bomb. I will let you decide that. I go back and forth in my opinion of Heisenberg. However, the uncertainty principle is very, very interesting. There's another relationship with Heisenberg when it comes to time, which is also really fascinating. So he's definitely a powerhouse when it comes to science. How you feel about his politics is a conversation for you to have at a different time.
A familiar depiction of the atom shows electrons orbiting the nucleus like planets around the sun. This model is neither accurate nor useful. We no longer think of electrons as orbiting the nucleus, and we cannot predict their location with accuracy. A more useful model is the quantum mechanical view of the atom, which represents the positions of electrons in terms of their probability of being in a particular region around the nucleus. If we could show all positions for an electron with a specific quantized energy, the resulting picture would look something like a cloud.
That's a pretty important video. In the old days, chemists and scientists thought that electrons circled the atom like planets around the sun, and that's totally understandable. It's an early idea for the atom, all right? However, classical physics, which works really well for planets around the sun because gravity is the main force, that doesn't work very well when you have positive and negative charges. So negative electrons, positive protons. That's the electrostatic force. And electrostatic force means eventually electrons would basically burn the atom up. They would go off crazy or they'd collapse and stuff like that. It's a bad thing. So instead of having the planets around the sun idea, which is still used in a lot of classic 1950s nuclear chemistry kind of things, if you ever looked on The Simpsons and stuff like that, which is fine, what they feel is that really electrons have a probability field. And that's kind of like this big circled area here. Those little dots right there, those are places where the electron could be. That's the probable region in where the electrons are going to be. Now, sometimes the electrons could be over here, over here, over here. That darned uncertainty principle, we just don't always know. We know their energies really, really well, but we don't always know their probability. So the atom has gone through many transitions, all right? It hasn't been a stable kind of thing. We started with like the plum pudding kind of model where individual little atoms maybe ran around and there was some kind of interaction between them. Then we went to the Bohr model, which literally was n equals 1, n equals 2, n equals 3, stuff like that, but that didn't work out too well. And now we have this probability field, this shimmering kind of thing. Now, there's nothing wrong with writing it as the Bohr model. I completely understand, but do realize it's not very accurate. It's more accurate to have those little tiny dots around, but of course that's kind of frustrating and stuff to draw as a teacher trying to get an idea across, so obviously it's not used as much. The classical planets around the sun idea just didn't work. Gravity is different than electrostatics, positives and negatives. The things that are happening on the atomic world are quite different than the things that are happening in the world of planets and suns and moons and stuff like that. So it's a whole different thing. It was a great idea to start off, but not so well in the long run. So in this field, we've seen some huge names in science. Planck, Max Planck Institute, E equals h nu. Bohr did the sharp line spectra and stuff like that. De Broglie, 7-page thesis, I'm still jealous, but he saw that all particles have a wavelength. Schrodinger, oh my gosh, quantum mechanics is just huge. We haven't even begun to touch it. We're going to look at it a little bit more. Heisenberg, even though he was a Nazi, he did do the uncertainty principle, which is pretty freaking awesome. And Einstein, oh my gosh, he's one of the premier scientists of all time. These are the giants of quantum physics, and it might seem kind of intimidating and stuff to see them all here. But I want to remind you all at this point that all of these guys and the other women like Marie Curie who helped out, all of them are human. This is kind of a fun picture I found of Heisenberg and Bohr, and they were dining in Copenhagen in 1934. And you can see here they're having a good time, but what I'd like you to see, if you can see it, is the bottle of beer right there. That's Carlsberg beer, and I am not advocating for you to start drinking by any means. However, Carlsberg beer is still the beer that's around, and so you can see these guys are kind of hanging out, having some really nerdy conversations conversations, having Carlsberg beer, and drinking coffee, and all these kind of things. These dudes are just as human as you are, and myself as well, and stuff like that. So Heisenberg and Bohr did all the normal things they did. They all took Chemistry 221 or the equivalent at one time or another, all right? They didn't just start off with an instant, database of cool science things. They had to work through it. So they were all where you are right now. And I want to remind you of that because your great things, a lot of them have yet to happen, and they will happen soon. One of my favorite expressions, argue for your limitations and they are yours. So if you start arguing for the things you can't do, yeah, you're not going to do them, all right? They're not going to start happening. So try and remember this, all right? Some great things are going to happen in your world, and you could be one of the great scientists that I'll talk about one day. You never know, but don't limit yourself. Go after your dreams. Okay, Professor Hot, kind of getting a little crazy there. I apologize, but I'm always trying, you guys are pretty cool to me. Okay, back to your regular scheduled programming. Quantum mechanics has some real useful things when it comes to chemistry. Now, to do the actual quantum mechanics problems, you've got to have Math 254 kind of skills, calculus, all right? And it's all stuff you can do. But in this class, certainly the goal was never for you to know calculus before you took Chem 221. So we're going to look at the results of the equations from quantum mechanics and how those results can be used to place electrons around atoms and ions. And to talk about all this, we need to talk about what orbitals are and what shells and subshells are. And again, over on the right side, you can see some of the math models that are used, and there's some beautiful mathematics that can be pulled out of all this. But that's not where we want to go. We want to talk about the results of quantum mechanics, and there we can do that through a series of what are called quantum numbers. When you take quantum mechanics and you do the calculus, you end up seeing that orbitals, those little side things, actually are where the electrons hang out. All right. And orbitals, we're going to see, there's usually a lot of them. Orbitals are placed into subshells, and the subshells are further placed into shells. So orbitals are like, if you will, the room in a house. Subshells are kind of like the houses themselves. And you can think about shells as being like streets with houses on them. The shells have subshells, and the subshells have orbitals. The streets shells have houses subshells, and the houses subshells have orbitals or rooms inside them. And again, the orbitals are what going to hold the electrons and stuff inside. The shells are called, I have given a special name, they're called the principal quantum numbers, all right? And they literally are a number. So we're going to start using the symbol N for shell. And this is analogous to what Bohr did with the shell. N equals 1, 2, 3, 4, etc. Those are the same basic type of shell values we're going to use in this class. The principal quantum number will help us to determine the energy and size of the orbitals and subshells. So just like some streets are more popular than others, some shells will have more energy than other shells. It's really kind of interesting how this stuff all works out. Periodic table is actually based around these quantum numbers. Now we're going to see that with a little bit of exception here, the N equals 1 shell is going to have just hydrogen and helium, only those two elements. And the N equals 2 shell is going to be lithium through neon. And you can see N equals 3, N equals 4, and stuff like that. So the shell number is something you can actually see in the modern version of the periodic table. The period number on the periodic table is kind of where the shell is. And there's a few exceptions to it, and we'll talk about that. But it's kind of cool to see how the shell number is actually related to the period number on the periodic table. So there are these 4 quantum numbers, and if you know the quantum numbers for the electrons, you can figure out some really cool things about them. You can figure out the shape, what the kind of looks like, size. You can figure the energy and stuff like that. Very, very cool. So these quantum numbers, which are the direct result of the calculus from quantum mechanics, can tell a lot of information about the electrons. So let's look at what the 4 quantum numbers are. First of all, there's N, the shell number. And that's the one that comes from Bohr. And the shell, which is always a whole number, is really going to help us find the energy and the size and stuff like that. N is, like, again, kind of like a street with houses on it. All right, the N shell is going to be pretty important. L and M sub L are called the subshell and orbital, respectively. L is called the angular quantum number, and it relates to the subshell. So you're going to see that there are different kinds of houses, and the houses relate to the L. And just like houses look different, subshells will have different shapes, and we'll talk about that, but it's the L value that helps out. Now, M sub L, the magnetic quantum number, actually is what's going to be used to tell which orbital we're talking about, which orbital is within a subshell. And the magnetic quantum number can help you figure out the direction that the subshell is facing, and we'll talk about that a little bit. The 4th quantum number is called M sub S. It's called the spin quantum number, and it's going to help us figure out the spin of the electron. Electrons, we're going to see, spin either, if you will, like this way, or they spin the other way. And one way is given a positive 1/2, and the other one is given a negative 1/2. Spin is important, but we're going to focus more on spin in Chapter 6, Part 2, the next section. What we're going to do in this part, we're going to focus big time on N, L, and M sub L, and how they can be used to start putting electrons around atoms. The quantum numbers handout, which is in the companion or it's on the website, might be helpful. It's an overview of the NL, M sub L, and I believe M sub S quantum numbers. So it might help you while going through this if you get confused or if this stuff is brand new to you. Here's a little bit more breakdown on N, L, and M sub L. So N, the shell number, we already seen starts at whole numbers, starts at 1, and it goes in whole numbers up to, in theory, infinity. And the N value helps us to understand the size and the energy of the different systems. L, the angular quantum number, depends on N. L always starts at 0 and goes up to N minus 1. And we'll see examples of this here coming out. But anyway, the angular quantum number is really called the subshell, and it helps us to figure out the shape of the orbital, like what it looks like. And again, just like houses have different shapes, we're going to see that the subshells have different shapes as well. And then finally, to figure out the rooms in our house, or the number of pieces, if you will, in our subshell, we need the orbital. And M sub L, the magnetic quantum number, helps us out with that. So the magnetic quantum number, M sub L, depends on L. These are L's right here. And what that says is M sub L goes from minus L to positive L in whole numbers. So let's say that you had an L of 1. M sub L would be negative 1 to positive 1. M sub L would be negative 1, 0, and plus 1. The number of orbitals in a subshell equals 2L plus 1. So just a second ago, when L equals 1, I said there was M sub L of negative 1, 0, and plus 1, 3 values. Well, 2 times L plus 1, 2 times 1 plus 1, 3 orbitals. That's a quick way to get the number of orbitals when you know the L. But if nothing else right now, do realize that M sub L depends on L. If you don't know L, you can't really know M sub L. And L also depends on N. If you don't know N, it's hard to know what L is. You can make some kind of blanket things, but it's hard to know. And again, M sub S, which is the 4th one, we're going to look at in the next section. A common thing we'll look at in this section is how to tell which set is not a valid set of quantum numbers, all right? And here's the kind of things you want to look for. First of all, when you always start with n has to be a whole number larger than 0, and you can see for A, B, C, and D, those are all whole numbers, so that's not a problem. Now, L is the next one, and L has an n dependence, and L always starts at 0 and goes to n minus 1. All right, so for example, if n equals 4 on A, then L would go from 0 up to 3. So L would be 0, 1, 2, and 3, and L of 1 is one of those, so that's legit. If you go to the B there, L of 5 is okay, because if n is 6, L goes from 0 up to n minus 1. 6 minus 1 would be 5, so L of 5 is okay. But the third one, n equals 2, L goes from 0 up to n minus 1. If n equals 2, n minus 1 would be 2 minus 1, 1. L of 2 cannot exist when n equals 2. L can be no bigger than n minus 1. So the problem here is C. This is the quantum mechanic way to describe L. Sometimes it's just a regular L, like it is down here with Emsabel, but the same idea. N and L cannot be the same. L can be no bigger than n minus 1, and that's important. Now, even though we didn't need to talk about it, let's talk about Emsabel as well. Emsabel has to be between negative L and positive L in whole numbers. So if L equals 1, Emsabel could be negative 1 like it is, 0 and plus 1. Those would be allowed values of Emsabel. On the next one, if L equals 5, Emsabel could be any number between negative 5 and positive 5, and 0 does count here as an example. On the next one, let's assume L of 2 was legit, so Emsabel would be somewhere between negative 2 and positive 2, so positive 1 is okay. And the last one, L equals 2, same thing, negative 2 to positive 2, negative 2 is legit. So those are the kind of things we'll be looking at when it comes down to these quantum numbers. In this slide, we're actually seeing what some of the rooms and some of the houses look like in chemistry, when you put electrons around orbitals. And this is pretty cool. Now, I'm going to circle here some of the subshell / houses. And every one of these kind of tan combinations, these are all subshells. And notice how, remember I said how a subshell is like a house. Well, some houses have just one room. So this big purple thing, that's a room. That's an orbital in the 3s subshell. On the other hand, right next door is a little bit fancier house. This house has 1, 2, 3 rooms in it, 3 orbitals in the 3p subshell. So if this was a house, this would be a 3-room house. The 3s house, on the other hand, would be a 1-room house. And on the far right over there, these are the 3D house, if you will. There are 5 rooms, 5 pictures right there. Those are the 5 orbitals in the 3D house. So each of those things I just circled, plus the ones below it, like 2s here and 1s, etc., those are the subshells, all right? And some subshells have just one orbital. The left-hand side is an example of that. Some of the subshells, like the 2p and the 3p, have 3 orbitals, and some, like the 3d, have 5, and there are other kinds as well. So these literally are the pictures of the room's orbitals, if it's an individual, or the subshells. If you combined all the 3p little orbitals, that would be the 3p subshell, that house, and that's pretty cool. Now, to talk about all of these, you can see there's like a number and a letter. And this kind of system is called the NL notation. The number that's in front is the n value. So for like 3s, that means n equals 3. The L value, as we saw in the last example, also has a number associated with it. But if you put a 0 or a 1, it might look like 30 and 31. It would be hard to tell. So people have developed this little acronym, stupid people drink freaking gas. Don't drink gasoline, kids. But anyway, each of those letters is associated with an L value. So for S, stupid, all right, that's the S, that means L equals 0. So for 3S, when you see 3S, that means N equals 3, L equals 0. On the other hand, this one right here, these are the 2Ps. So if you wanted to know 2P, the 2 is the N equals 2, and P, the people of this little acronym, means L equals 1. So it's really important that you know how to find the N and the L value. The N is easy, it's just the number. The letter, you have to figure out what it stands for. And there's different versions of this. Stupid people drink freaking gas. Stupid people drive freaking gas hogs. If you want to go H5, which is down below. All of these are good, but you do need to know what number is associated with the letters. Make sure you know / memorize that. Here's a question where it says a certain orbital n equals 3, L equals 1, m sub L equals -1. What type of orbital is this? Good. So this is the NL notation. N of 3 means the first number will be 3, so it definitely won't be answer D. And what we have to do is figure out what L equals 1 means. So if you go over here to this little diagram, L equals 1 is P. This should be a 3P, or answer C would be right. If it was 3S, you would have L equals 0. If it was 3D, you would have L equals 2. So you can hopefully quickly interpret what the NL notation means in terms of N numbers and L numbers. When n equals 1, L, which is only from 0 up to n minus 1, L can only be 0. And if L is 0, m sub L, which goes minus L to plus L, can only be 0. What this means is that in the n equals 1 shell, there is only one subshell. So n equals 1 is where I got the n equals 1 shell. There's only one value of L. That means there's only one subshell. So L equals 0 doesn't mean there's no zeros, right? That's a legit value of L, and that means there's one subshell. And because there's one allowed m sub L value, and again, m sub L of 0 doesn't mean there's not one, that's one allowed value. M sub L of 0 means single orbital. So you can quickly tell that in the n equals 1 street, there's one house, and that one house has one room. In chemistry, the n equals 1 shell has one subshell. That's an S subshell, by the way, from the SPDF thing. And that one S subshell has one room, and m sub L equals 0. And this is how people figure this out. This is the 1S subshell. S comes from the fact that S's kind of look spherical, like a big sphere. And people that know more German than I do say that sphere is sphere, whatever, and spherical spherisch. Okay, and again, I'm the worst. I can't even do English, let's be honest. But anyway, that's supposedly where the S comes from. So all of the S's, 1S, 2S, 3S, as we're going to see, are basically spheres. If you look back at that last picture on the far left, all of them were basically spheres. Now, if you've seen in chemistry electron filling orders like 1s2, 2s2, 2p6, that kind of thing, this is the 1s. And you now see that it came from quantum mechanics. 1s means n equals 1, L equals 0. You know that those are legit rules. We're going into this a little deeper than you may have done before, but it's all stuff you can do, and that's kind of cool. Here's some pictures that kind of show a little bit more what's happening. Now, S orbitals always have L equals 0. SPDF means L equals 0. And so S orbitals are always spherical, okay? And so if you look at these pictures right here, this is like a side view of what it looks like. And you can see that at a certain point, it just gives out, all right? That's basically a sphere. And you can also notice maybe that right here it says R90. That's a probability that the electron will be inside there 90% of the time. And usually that's pretty good. I talked earlier, a long time ago it seems like now, about nodes. And nodes are places where there's no electron density or no wave. And we start seeing spherical nodes when the orbitals get bigger and bigger. A spherical node is like a ball within a ball. And that ball within a ball is where there's no electrons. And spherical nodes, you can calculate them using n minus L minus 1. So this video that's showing right here, there's like color bands, but inside the bands there's some black lines. Those black lines are the spherical nodes. If you have a 6s orbital and you want to know how many spherical nodes there are, you better know the n and L values. So 6 is the n, that's the 6 right there. S is L equals 0, that's that one right there, and n minus L minus 1, this thing has 5 spherical nodes. So we're going to talk a lot about types of nodes when it comes to these crazy subshells and orbitals. And n minus L minus 1 is the way to find the number of spherical nodes, and we'll come back to that later. This is the 1s orbital, all right? It's in the 1s subshell. The 1s subshell has just one orbital, and you can see in the middle there, that little kind of shiny stuff, that's in the middle of that diagram. That's the actual 1s electron, all right? And really it's a shimmering sphere because it represents 90% of the electron, blah, blah, blah. Speaking of probability, psi star is the way they find the probability, all right? And you can tell there that if you take that, that's how they find these 90% confidence kind of things. Now, no spherical nodes. N minus L minus 1 would be 1 minus 0 minus 1, 0 spherical nodes, nothing in the 1s orbital. Notice how small the 1s orbital is. The 2s orbital is bigger. The n value is proportional to the size, more or less. So 2s is bigger than 1s, 3s is bigger than 2s, etc., etc. If you look in this two-dimensional representation on the right-hand side, there's like a white circle in the middle of a dark black circle and the other black stuff around it. That's one of the spherical nodes, and it's represented right there in this graph. 2s has one spherical node. It's like a node with a sphere within a sphere, and on that sphere you have no electron density. So n minus L minus 1, n is 2, L is 0, so 2 minus 0 minus 1, one spherical node. And that's what you're seeing there in the middle or in the graph. So it's kind of interesting. So again, 2s is bigger than 1s, but again, it's basically a sphere, one spherical node inside there. That's kind of important. 3s is bigger yet, all right? It's even bigger than 2s and is getting bigger. You went from 2 to 3. There's 2 spherical nodes, which you can see in those little graphs there on the right. My little animation in the lower left is kind of mesmerizing, but there are actually 2 black line kind of spheres in there, and those represent the spherical nodes. So it's kind of cool to see. 4s, of course, would be bigger yet. 5s would be bigger, and every time you raise an n, you have one more spherical node. We talked about n equals 1, what happens then. Let's now talk about n equals 2. Now when n equals 2, you have 2 possible values for L. Remember, L goes from 0 up to n minus 1. So that means that allowed values of L will be 0 and 2 minus 1, 1. So when n equals 2, you've got 2 L values. Now let's break that down into some language. The n equals 2 shell has 2 subshells, the L equals 0 subshell and the L equals 1 subshell. The n equals 2 street has 2 houses on it, an L equals 0 house and an L equals 1 house. This is kind of how this stuff all begins to play around. Now, we've actually already seen the L equals 0 part. We'll talk about that. But there are 2 types of subshells, 2 types of orbitals, and each subshell has its own type of orbital. The L equals 0, which means M sub L equals 0, this is the 2s subshell I showed you a picture of. So remember that if L equals 0, M sub L goes from negative L to positive L, so that's only L equals 0. If L equals 0, that's an S, so this is going to be the 2s subshell, and that's one we saw a picture of earlier, no problem. But the other possibility is when L equals 1. When L equals 1, it's a different game. M sub L goes from negative L to positive L. So if L is 1, that means M sub L is going to be negative 1, 0, and plus 1. Those are the 3 allowed M sub L values. And so what we would say is there's going to be 3 orbitals because of the 3 allowed M sub L values. And if we're going to designate this, still at n equals 2, but now L is 1, that's going to be a 2p subshell. So this is the first time now that we've seen a 2p subshell. There was not a 1p subshell, all right? There was only the 1s. But when it comes to n equals 2, we've got a 2s and a 2p. And the 2p has 3 orbitals in it. You could think about it that the 2p house has 3 rooms inside it, while the 2s house had just 1 room. So the 2p subshell is a little bit more elaborate, if you will, than the 2s. Planar nodes are another type of wave phenomena that occur when you have different combinations of orbitals. And planar nodes we're going to see are equal to L. So when L equals 1, you can see there's like this line, this sheet of glass that goes down the middle that separates the two of them. That's a planar node. Planar nodes equal L, and all p orbitals have a planar node that goes right through the nucleus. Here's a better representation of those planar nodes. You're going to see that there were 3 M sub L values, and you can think about the M sub L's. This isn't quite correct, but it works for this conversation, okay? The M sub L values, negative 1, 0, and plus 1, all right? And so those represent the 3 orbitals in each of those M sub L values. And that sheet of glass will literally go between the orbitals. Notice that all of these look kind of like a figure 8, all right? And so the plane of glass goes right through the middle. So in this case, you can see it's in the first one, it's in the YZ node, and the second one, the XZ, et cetera, et cetera. But they all have a planar node. Also importantly is that they're all at 90 degrees. So the X, Y, and Z is no accident. It's considered to be an X-axis, a Y-axis, and a Z-axis kind of plane. So you can see that if it's X, then that figure 8 is right along the X-axis. And if it's Y, it's right along the Y-axis. And of course, the Z up and down, traditionally up and down is the Z-axis. So you're kind of hopefully seeing how this stuff all works out. So again, s orbitals are in the s subshell, and there's only one of them. But if you do have a p subshell, then there are 3 p orbitals, and one you can think about as x, y, and z. Kind of cool. 2px is just a p orbital aligned along the x-axis. So you can see in the picture right here, this is the x-axis, and here's that figure 8. Now notice there's a planar node. It separates the 2 nodes, the 2 lobes of the p orbital. Pretty cool. I'm having it rotate there because I guess it looks kind of pretty. Now 2py and 2pz would be very similar. If it was 2py, it would be along this axis. And you can imagine if this was a 3-dimensional graph, there would be a z-axis right here, and that would be along the z-axis. But they're all basically the same. They're just at 90 degrees from each other. 3px is bigger than 2px, just like 2s was bigger than 1s, but 3s was bigger than 2s. So again, 3px means that most of the interaction is going to be along the x-axis, and it looks more or less like the figure 8. But we're running into, first of all, the planar nodes. Planar nodes always equals L, but remember that spherical nodes equal n minus L minus 1. So spherical nodes nodes for 3p would be 3 minus 1 minus 1, one spherical node. And oh my goodness, so you've got this kind of thing going around here. That's the spherical node as well. So using NL, you can find spherical nodes. Using the L values, you can find the planar nodes. And again, 3py would be similar. It would just be along the y-axis, and 3pz would be similar, but along the z-axis. How many total nodes in a 4p orbital? And you have those possibilities right there. So before we do that, let's figure out what n and l are for the 4p. So 4 is the n, all right? The number literally is the n value, so that's good to go. P, it goes SPDF for 0, 1, 2, 3, etc. P is the second one, so P means that L equals 1. Now, when it comes to total nodes, there are planar and there are spherical. And planar nodes just equal L. So if L equals 1, the 4p orbital would have one planar node. But there's also, remember, spherical, and spherical n minus L minus 1. So here n is 4, L is 1, we subtract 1 on top of that, n minus L minus 1, 2 spherical nodes. So there's one planar node, 2 spherical nodes. There's a total of 3 nodes total, sorry. Planar nodes, as I said, equals L. Spherical nodes, n minus L minus 1. So there's one planar node, there's 2 spherical nodes, add those up, 3 total nodes. So this is a good question because it forces you to find, of course, the n and l values from a certain NL designation, and then you can find planar nodes and spherical nodes, put them together, good to go. D orbitals are when you run into L equals 2. And we haven't seen D orbitals when n was 1 or 2. Remember, n equals 1 had just one s. N equals 2 had 2s and 2p. But we haven't seen D at all yet. So when n equals 3, what are the values of L? L always goes from 0 up to n minus 1. So if n is 3, that means L is going to be 0, 1, and 2. Those are all allowed L values. Each one of those is a subshell. There's going to be 3 subshells in the n equals 3 shell. When L equals 0, M sub L is 0. L of 0 is an S. This is the 3S subshell, and it's similar to 1S and 2S, just bigger with more spherical nodes. It has a single orbital. When L equals 1, M sub L goes from negative L to positive L, negative 1, 0, and plus 1. These are the 3p orbitals. So the 3p subshell has 3 orbitals, x, y, and z is the way you can think about it and stuff. No problem. And 3p bigger than 2p, but otherwise pretty similar. But the new player now, when you get to n equals 3, is L equals 2. If L equals 2, M sub L goes from negative L to positive L. So that means negative 2, negative 1, 0, plus 1, and plus 2. Those are the 5 allowed M sub L values. That means there's going to be 5 orbitals in the 3D subshell. So again, you can think about the 3D subshell as like a type of a house. And this type of house, subshell, has 5 rooms, 5 orbitals. So it's a little bit fancier kind of house than we've looked at before. The L equals 0S house had just 1 room, 1 orbital. The L equals 1P house had 3 rooms, 3 orbitals, but woohoo, this L equals 2 house has 5 rooms, 5 orbitals, even cooler. So d orbitals, when L equals 2, all right, are kind of cool. S orbitals have no planar nodes, and so they're spherical. The p's had one planar node. They're dumbbells, figure 8 shaped, infinity, whatever you want to call them. D orbitals, you can extend it out too. Now, d orbitals are going to have 2 planar nodes. L equals 2 means 2 planar nodes. And what most of these look like are like 2 big p orbitals. Like the darker purple one there, that's like 1p, and the other kind of lighter red one, that's the second p. And you can have literally 2 sheets of glass, 2 planar nodes, kind of bisecting them like that. So most of the d orbitals look kind of like 2 figure 8s, 2 of the p orbitals squished together, but they will have 2 planar nodes one way or the other. Remember, planar nodes equal L, and spherical nodes n minus L minus 1. So this is an example, a picture of the dxy orbital. You can see that there are 2 sheets of glass going through it. That's because if you have L equals 2, you will have 2 planar nodes, 2 pieces of glass, and you can cut them through those figure 8s more or less. Here are the px, py, and pz's. Those p's have 1 planar node, L equals 1, but the d's will have 2 of them. All right, it depends which one you look at, but they're basically separating the nodes together. So instead of having just one thing of it, it's like you're combining 2 of them to have 2 of them. I don't know if that works for you, but it works for me anyway. This is the 3D XY orbital, all right? And the 3D XY, if you look at the picture on the left, one of them is kind of between the X and the Y, and the other one is on the opposite side. But again, 2 spherical, thanks for playing, 2 planar nodes are inside there, all right? And you can see it's shimmering and stuff like that. N minus L minus 1 is the way to find spherical nodes. 3 minus 2 minus 1, these don't have any spherical nodes. They will have planar nodes. L equals 2 means 2 planar nodes, but they don't have any spherical nodes. This one is the 3DXZ, all right? So you can see again how you have kind of like 2 of these figure 8s, and they're between the X and the Z axes and stuff like that. But again, they look very similar, just different axes. This is 3DYZ. So again, those figure lobe things are kind of between the Y and the Z, and they rotate around, looking pretty cool. The 3D Z squared, I always call the donut orbital, and that's not really accurate, but it is kind of fun to think about. These guys have a harder spherical or planar node, to see, but you can see here in this 2-dimensional picture, there are literally 2 of them kind of bisecting it and stuff inside, which is pretty cool. So this is the 3D Z squared orbital, and then there's also the 3D X squared minus Y squared, and this orbital is right in the X and the Y plane. So you can see this one's right along that axis, and this one is right along that axis. So pretty similar. And again, 4 of the 5 of them look kind of like 2 p orbitals squished together. The donut shaped is a little bit different. Here's an example I want to do with you. I want to go through the n equals 3 shell, and we're going to talk about how to get all these values, and I encourage you to, if you want, you can pause this video, see how many of these little pieces you can fill in, and then we'll go through and fill them all out for you. So then n equals 3, L values, L goes from 0 up to n minus 1. So if n equals 3, that means L is going to be 0, 1, and 2. Those are the 3 subshells when n equals 3. And those are going to have a letter we'll see associated with them as well. But again, when L goes from 0 up to n minus 1, 0, 1, and 2. Now, each one of those L values has a letter, and it goes S, P, D, F, G, H. After that, S, P, D, F are honestly the most important ones. So L equals 0 is S, L equals 1 is P, L equals 2 is D, etc., etc. So for NL notation, which is n number first followed by the letter L, you would have 3S, 3P, and 3D. That would be the way to designate the different subshells from each other. Now, m sub L has to do with the number of orbitals, but we're just looking for the raw numbers here of m sub L. M sub L values go from negative L to positive L. So for example, for the 3s, L is 0, negative 0 to positive 0, there's only going to be an m sub L of 0 for that one. But when it comes to 3p, L of 1, negative 1 to positive 1, the m sub L values will be negative 1, 0, and plus 1. And for L equals 2 over there, you'd have everything from negative 2 to positive 2. So these are the m sub L numbers. And you can see how it goes 1 m sub L value to 3 m sub L values to 5 m sub L values. Quantum mechanics is filled with patterns. So just FYI, you're going to see a lot of them, and this is one of them. Now, each one of those m sub L values is an orbital, even 0. 0 is legit. That's a legit value. So if you have m sub L of 0, that's going to be 1 orbital. If you have m sub L negative 1, 0, and plus 1, those are 3 orbitals. And of course, the last one would be 5 orbitals. So there's lots of different ways to do these kind of things. The total number of orbitals, if you count 1 plus 3 plus 5, you'll see that it's 9. A quick way to do this is that if you have the n value, n squared is another way to find the total number of orbitals. So n equals 3 is what we started with, 3 squared, 9 orbitals total. But now you can see kind of like where they all come from, and that's kind of a cool thing. Some people like using the train track model to represent this, and that's fine too. Up here on the top in red, these are the n values. So there's n equals 1, n equals 2, n equals 3. And like we saw, if n equals 1, there's only L of 0, which is the s, and the L equals 0 has just one m sub L value, one orbital. So that's the 1s orbital in the 1s subshell. On the other hand, when you get to n equals 2, then L values are 0 and 1. They always go up to n minus 1. L of 0 is just an s. That's the 2s. But when L is 1, then m sub L, negative 1, 0, plus 1, those are the 2p orbitals. And then over here, you can do the same kind of thing. This would be 3s. These would be the 3p, and these here would be the 3d. And you can do this for all of them. It works really well. Just make sure you figure out a way to make this all work in your head. There are f orbitals too, and we're not going to spend as much time on them, but when you get to n equals 4, you've got L values going from 0 up to n minus 1, so that means 0, 1, 2, and 3. So there are 4 subshells, 1, 2, 3, 4 values of L. So that means 4 subshells in the n equals 4 shell. The first one, when L equals 0, m sub L equals 0, that's just the 4s subshell, and there's a single orbital. When L equals 1, m sub L goes from negative 1 to positive 1, so there's 3 values of m sub L. This is the 4p subshell with, again, like we've seen earlier, 3 orbitals inside it. L equals 2 at this point means m sub L goes from negative 2 to positive 2, 5 m sub L values, 5 orbitals in the 4d subshell, and the new player on the block, L equals 3. If L equals 3, m sub L, negative 3 to positive 3, those are 7 possible values. This is the 4f subshell with 7 orbitals. Now, a lot of times they don't even show pictures of these, but I think it's kind of cool. These are the best pictures I could find of the different f orbitals, and they're pretty cool looking. They more or less look like, depends on the orbital and stuff like that, but more or less there's like, oops, let me draw here. There's like 1 of the p orbitals, there's 2 of the p orbitals. They more or less look like 3 p orbitals squished together. Some of them have the donuts and stuff. There's some really cool kind of chemistry going on, but again, we're not going to focus so much on the orbitals, but it is kind of fun to see what they look like. And if you have to make a guess, 3 of those p orbitals squished together would be a good thing. Now, L equals 3 for these, they're all going to have 3 planar nodes too, which is kind of neat. We're almost at the end of this section, and I want to talk about some things we talk about that'll help make this material easier. So this is kind of a quick and dirty overview. I highly recommend that you memorize both C and H. We're going to use both of those constants a lot. The speed of light equals wavelength times frequency. Planck's constant is essential for energy, so they're both going to come in really handy. And speaking of electromagnetic radiation, the visible light, ultraviolet light, radio, gamma rays, etc. E equals h nu, which equals hc over lambda. Nu is in frequency, which a lot of times has units of hertz, which just means 1 over second. This is the de Broglie equation, and in this case the wavelength of the particle is equal to Planck's constant divided by the mass of the particle times the velocity of the particle. So that wavelength is only for particles. The wavelength up here was for the electromagnetic radiation, gamma rays, etc., etc. Now, down here I have some information on the quantum numbers. The number of orbitals in a shell is going to be equal to n squared. The number of orbitals in a subshell, 2l plus 1. So if you have just the n and you want to know the number of orbitals, n squared. If you have the subshell, then 2l plus 1. The SPDF notation is important because you need to know the L value that goes along. Here's yet another one. Stupid people drive freaking gas hogs. Oh, there's a whole bunch of these. A 4D subshell would have n equals 4, L equals 2. Planar nodes and spherical nodes important. Planar nodes equal L. Spherical nodes equal n minus L minus 1. And if you can do these things, this chapter is going to be a lot easier for you. So make sure you know this kind of information. You will be good to go.
Zeiss's salt is a compound made from platinum chloride and ethylene. The ethylene cannot bond to the platinum unless orbitals in the two fragments are oriented properly to each other. This alignment occurs most effectively when the ethylene is perpendicular to the molecular plane of the platinum chloride fragment.
Finally, I have to leave an example as how important these are. This is an example of a platinum metal reacting with some carbon, and the platinum has the d orbitals, the two figure eights kind of around it, and the carbons have basically p orbitals. And you can see at first like the atoms couldn't make connections. Making a bond between two atoms is basically about the electrons coming close to each other, making a handshake. And if they were oriented incorrectly, you don't have any handshakes, any overlap, so they have to be in the right connection. So bonding in molecules is essentially a result of these atomic orbitals being in the right position. And if you know how it is, then you can explain the bonding like you're seeing in this example right here. We'll talk more about that in Chem 222. Okay, but that's it for this section. Thank you for spending your time with me. If you'd like to look at some more examples, Chapter 6, Part 1 Study Guide is a bulleted list that will help you through, see the important concepts. Concept guides, which are also available, will help you see some worked problems, especially like on frequency, wavelength, and stuff like that. Right after this slide right here in the lecture notes, you'll be able to see the important equations that I think are good. And also after that, there are some end of chapter problems. So several questions. The answers follow on the next slide. If you can do these kind of things, you've got this going on. If you do have questions on any of this, please reach out to me. I'm more than happy to help you. This is kind of weird stuff like we've talked about, but it is all stuff you can do, and I want you to remember that. Okay, good luck with your studying, and have a wonderful day.